Okay, welcome back for the second session of the course by Alessandra. We talk about tensor decomposition.
Good morning. Welcome back. So I'm gonna keep continuing on what we've seen yesterday. This is more recap of what we've seen. As we said that we start very basic. We define as tensors. We define the tensor rank to be the minimum R that we can write your tensor as the sum of R rank one tensor or simple tensor or like elements in the image of some map. And then we realize that there can be two different notions, for example, of rank, that is the visual rank, but we also use the border rank to be the minimum R, such that your tensor belongs to the R secant variety, to this guy here that was the Segre. So the Segre is the variety of rank one tensor, and this is the closure of tensors of rank at most R. And we saw an example. The baby case was the W tensor of order 3. That guy happened to have rank 3 but border rank 2 because it was the limit of a sequence of rank 2 tensors. And so the border rank is always smaller or equal than the rank of the same tensor. For certain tensor you have equality, but for example the W tensor tensor. And then we've seen that they can define the Segre variety, namely the variety of rank one tensor, by taking all the 2 by 2 minors of all flattenings. And by flattening, I mean that I can really flatten my tensor in all possible directions, and I can make a partition in 2 subsets of subindices of the whole string of indices of my tensor. And for any of this partition, I get a linear map, and the 2 by 2 minors of all this linear map that define ideally theoretically that the Segre variety. And then we pass to symmetric tensors, because it's what we can do something. So if you are really interested in computing the rank of your tensor, the first step is like pass to symmetric tensor, and the very easy case that are tensors of that belongs to C2 tensor C2 tensor C2 d time. And so we pass to symmetric tensors. We define what a symmetric tensor is, and then we define the symmetric rank. And the symmetric rank has almost the same definition of rank, except that instead of having just a sum of R rank one tensor, you also impose that this rank one tensor, they have to be symmetric. Okay? And at the state of the art, we still don't know if these two numbers are the same. For sure, you need less tensors of rank 1 if you don't impose the condition of being symmetric. So one inequality is easy, the other inequality is still an open question. I mean, in general, as a general question, there are many examples where it is known that they are the same. And then if we rank one tensor with the condition of being symmetric, we have the Veronese variety, and the equations of the Veronese variety are the 2 by 2 minors of all the flattenings, but now you start with a symmetric tensor, not just with any tensor. Okay, so that's more or less what we have seen yesterday. Are there any questions on what we seen yesterday? I can't hear. Can you speak loudly?
Taking connection to my last lecture yesterday, there was a setting which we defined genus polynomials. We also said that there's one-to-one correspondence between polynomials and symmetric tensors.
Yeah, but it's not the same thing, because it passed from homogeneous to non-homogeneous. So it's like to pass from the affine space to the projective space. Okay. Here I'm really saying I start with some symmetric tensor, and I make a one-to-one correspondence with homogeneous polynomial of degree d. And then you can dehomogenize if you want. But the map of Bernardi was really the dehomogenization, so projective to affine. This is just a correspondence as vector spaces. I'm just taking two vector spaces, the space of symmetric tensor and the space of polynomials, and I'm just making a one-to-one correspondence between them. Other questions? Okay, so let's start. So now I start introducing some tools that will be useful to compute. So now my goal is to compute the rank of symmetric tensor of type C2, 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 namely in terms of homogeneous polynomial of degree, any degree D in two variables. Okay, and now I start introducing some tool. The first tool is something that yes, we have seen also yesterday with Bernard, but I'm using a slightly different language. So it's really very similar, but it's actually the same thing for some parts, but it's a slightly different language. Okay, so I want to introduce these maps. They're called catalectical map, and I'm doing this with an example. And so the example I take, so I take in this case, I have the Veronese variety. I start with P2, so I have three variables, okay? And I embed this P2 with degree 3, so I'm having a polynomial of degree 3 in three variables, and that's its ambient space. And I define this map that goes from partials, I have three variables, okay? And I decided to start with partial of order 2, okay? And then how it acts? Well, it acts by applying the partials on the polynomial you started with, okay? So the map takes some partial and it applies to your polynomial, okay? In this example, my f, I didn't write it, it was like x to the cube, and so it applied. So, and if I start with a polynomial of degree 3 and I apply partial of order 2, I end up with a polynomial of degree 1. It's homogeneous, so everything is fine. Okay? So I apply partial of order 2 and I get and I evaluate this partial. Okay? And I think I have, yeah. So okay, you can, I mean, it's a linear map, you can fix bases. Okay, you can fix bases and produce some metrics. And in this example, I just wrote any polynomial of degree 3. This is the same map as I wrote before. I fix some bases over here in the domain. I fix some bases in the domain, and this is the output of my polynomial. And so I can write like a matrix. And after having fixed the basis, I can write the matrix associated to this map. Okay. So there are various things that I would like to stress. I made a choice of basis in order to write this matrix, okay? So you can make like smarter choice of basis or not. So this is these are both space of polynomials, okay? And so you may fix the basis that is the monomial basis, but for example, when you raise this power or when you make the partial, you get this coefficients. Then depends on the problem that you have to deal with. You want to stock the coefficient in the basis or maybe not, okay? And this is something, or maybe instead of working with exactly with partial derivation, sorry, I keep going back and forward. Instead of really doing the partial, you may do contraction. Okay, if you do contraction instead of doing partials, then you don't have to deal with these coefficients. And I think that this is more or less what Bernard did it yesterday, because he had to divide by all these coefficients when he made the polar plot. Or maybe you'd better working instead of working on the space of polynomials, you may work on divided powers, and then you'll get rid completely of all the coefficients. Okay. These are more computational aspects. I don't really stress too much on this. I just want you to keep in mind what we are doing. We are essentially doing partial derivation. We can stop your problem of coefficients in the basis, or doing contraction or dividing powers. It's more, my point is that now I want to do like partial derivation. Okay. So the other thing that I want to stress is that I did I built this matrix as a matrix associated to the previous map that I called catalytical map in some basis. And now if you think that I stopped the coefficients in the basis, this looks like this map. And I don't know if you remember this from yesterday. This is one of the flattening that we did yesterday on one of the symmetric tensors. Okay, so doing this partial derivation is exactly the same thing as doing some flattening. And that's not surprising because when you do partial derivation, if you forget the coefficients, you really get the coefficients of your polynomial. Okay. Okay, so this is, I mean, I just rewrote the same thing. This is the matrix associated to the previous, this is C21, sorry. This is the catalytical matrix that represented the map before, and this is the flattening. They are exactly the same thing. So how do I define in general these catalytical maps? So I fix a polynomial of some degree. I mean, I can define catalytic. I will use them for the polynomials in two variables, but I can define it for any number of variables. So I might fix my homogeneous polynomial of some degree, and then I define them by taking the space of partials of some order, and I evaluate this partial on my f, and so I end up with polynomials of degree d minus the order of the partial. It's homogeneous, and so this is true. They are linear maps. They have some associated matrices. I call them catalytical matrices. They happen to be symmetric, these matrices. And these are, I don't remember if Bernard arrived already to this yesterday, but so we will probably see this today. I think it will define it like in a transpose way by starting from, I mean, really the transpose of this, but they are symmetric. So I'm still happy with this thing. And these matrices, as I defined them, they are defined for all I going from 0, not 1. I can also not making any partial up to the degree of f. And of course, I have different sizes. Okay, so in dependence on the order I take, I have different space of polynomials in the domain, and they have different sizes. I know it looks a trivial comment, but it's kind of, at some point we will have to deal with this fact that they have different sizes. And as I said, I mean, this first catalyticant, when I go from 1 to d minus 1, they corresponds to the first flattening that we have seen yesterday. So if it's true that this catalyticant, the first catalyticant is the same as doing the first flattening, well, I can also use catalyticant to test rank 1. Okay, because yesterday we said that rank 1 tensor are defined by the 2 by 2 minors of flattening. So if I can make flattening instead of this very complicated way of taking all the subindices, blah, 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 and divide it into pieces, and then I can also do catalyticant that are easy. I just do partials, first partial derivation, and then I can look at this rank, at these matrices. If they have rank 1, I'm happy. Okay, so I can use catalyticant to compute rank 1. Okay, so it's easy to know if a tensor is rank, if your polynomial is rank 1, you compute the first catalyticant. If its rank is 1, then your polynomial is rank 1, meaning it's a pure power of a linear form. Otherwise, the rank is bigger than 1. Okay, tensor rank 1 is easy. We are all happy on this. Okay, example, this is a rank 1 polynomial. I write down the first catalyticant, this is what I get. And after having fixed some basis, this is the catalytical matrix, and it's clearly of rank 1. Okay. This is not rank 1. Let's check it. This F is the sum of 3 cubes. I write down the. Yes, sir. I can't hear you, I'm sorry. Or simulation with that. And if you start it, for example, like with the then you have this many columns that are white. Other questions? Okay, so this is not rank 1, but let's check it. So I do the first catalectic, I pick some bases, and then I write down the matrix, and the matrix is not rank 1. And so I can just say this is not rank 1. Okay? This does not prove that it has rank 3, as it really looks like, but it's just saying that there's not rank 1. Okay, so there were already many other questions yesterday on these 3x3 minors, if they can define rank 2 or not. And we already have this hint on the W tensor. Okay, that is not going to work. So let's see what we can say from this case. So this is another example. This is clearly rank 2, but let's see what happens if I do my catalytic map. It is not rank 1, so it's not the rank 1 tensor, but you see it as rank 2. Okay? But if you want to test the 3x3 minors, you cannot test the 3x3 minors because of size. It's a matter of size. Okay? The matrix has rank 2, but you cannot test that the 3x3 minors are 0. Now, that the previous one was the catalytic that went from partials of order 1 to polynomials of degree 3. Sorry, yes, degree 3, it's degree 4 polynomial. And now we look at the next catalytic. The next catalytic goes from partials of order 2 to polynomials of order of degree 2, of the same polynomial. This matrix here still has rank 2, we like it, and now we can also test the 3x3 minor because it has a bigger size. Okay? So it's the same polynomial. The next catalytic matrix has the same rank. And now I can test, I have a way of testing with the minors. So the existence of 3x3 minors is just a matter of size. Okay? If I can compute that the 3x3 minors, it's just a matter of size. But what's an important fact is that as soon as you can, as soon as the size of your matrix is big enough to allows you to see the minors being 0, the minors of certain order of being 0, then the rank of this matrix is going to be always the same. If it's possible. Okay, it may be that your polynomial is a certain structure that there's no way to enlarge the catalytic matrix to see the minors being 0. Okay, but in principle, as soon as you have some all the minors of certain order being 0, this reveals the rank of this catalytic matrix, and if you keep increasing your catalytic matrix, it will keep the same rank. This is another example. Now I take a polynomial of degree 6 in 3 variables, and this is the first catalytic, and since I have 2 variables only, I cannot have more than 2 columns, and so whatever is its rank, I mean this catalytic has size 1, and a size as will have rank 2. Okay. And if I do the second catalytic now, I go from polynomials from partials of order 2 to polynomials of degree 4, and this space has dimension 3. And the rank of the catalecticant will be 3. And again, I don't see the 4x4 minors. And so if I do next the third catalecticant, I keep doing. And you see this will be the one that will have the biggest possible size to see some minors. Because from the next size, if I start doing the next one, so from the fourth to the second one, I really will have the transpose of the previous one. This one. Okay. So in terms of size, as soon as you reach more or less half and half, the degree of your polynomial, if it's even, it's easy. If it's not even, you have more or less half. And this is the most square catalecticant. So the one where you have more chances to find the biggest minor being 0 if it's possible. And again, if you look at this matrix here, it didn't write it, but it turns out to have rank 3. And in this, and it has size 4, and here you can see the 4x4 minors being 0. Okay? So this is big enough. This most square catalecticant is big enough both to see the rank and to see the killing of the minors. Okay. So the first one didn't have, the first catalecticant didn't have rank 3 because it has rank 2 and it only had 2 columns and it was not possible to have rank 3. As soon as you have room enough to have enough columns of having the right rank, you got it, and you can certify it's the right rank of the matrix as soon as you have the minors being. Okay. Okay, so the rank of this catalecticant is stabilized as soon as the size of the catalecticant is big enough. And so if you don't know in advance which is the rank of the catalecticant we are looking for, as we've just seen in this example, instead of start trying from the first one, the second one, and the next one, we just go in the most square one. And we see if it's true that this the rank of this catalecticant is stabilized after a certain time, you go to the most square one and you look at the rank of that. Okay. Okay. So we have already seen that the vanishing of the 3x3 minors of catalecticant tells us the border rank, but what can we say about the rank? And here I have collected the 2 examples. So this is a polynomial of true rank 2. And this is the same example I did yesterday. Someone yesterday asked me when I wrote the W tensor. I wrote in terms of really a tensor. It was like E0, E0, E1 plus E0, E1, E0 plus E1, E0, E0. And someone asked me, but this is symmetric, so it's a polynomial. Yes, it's true. It was not this one because this is of degree 4. So it corresponds to a tensor of order 4. And the one we saw yesterday was of degree 3, but it's, I mean, it's geometrically it has the same behavior. Let's see. So let's compute. They have degree 4. So the most square catalecticant is 2, 2. I start from partials of order 2 and I go to polynomials to degree 2. I write down the catalecticant, and this catalecticant has rank 2. And I like it. It has big size. I can also compute minors. And indeed, that polynomial has rank 2, and it's fine. Okay, this is rank 2, this polynomial is rank 2, and it's fine. What happens here? Here I write down there are some typos. This 2, 2 should be here. I compute the same catalecticant. And now this catalecticant, it has rank 2. Okay? And this is coherent with the fact that the 3x3 minors vanishes. And this is coherent with the fact that if that guy is a W tensor, then there's a sequence of tensors of rank 2 whose limit is that tensor. Okay, but as you have seen yesterday, this guy will probably not have rank 2. Okay, but the 3x3 minors, they reveal me just the border rank in this case. Okay. And so here I just say that the rank of F is clearly 2. Why? Well, the rank of this matrix is, can you tell me why it's clearly 2? Yes, but then you have to tell me that it doesn't have rank 1, because the rank is the minimum one, right? So it's clearly at most 2. So why is not 1? Right. So it's not 1 because this matrix has rank 1. Then it's clearly 2 because you have the good. Well, I cannot say the same for that because I don't have the presentation as sum of 2. So yeah, this is just to do the same thing we did yesterday in a slightly different way. So I want to prove now that there's this W, is the W tensor. It belongs to the tangent space to the rational normal part. No, this is P1. Sorry. Okay. It's not V4 or P4, but it's V4 of P1 of the rational normal quartic at the point x to the 4th. Okay, so rational normal quartic are quartic of linear forms. So this is a nice point of that curve. And I want to see how the tangent space is done. So I go in P1 and I take a line in P1. Okay, it's easy. And then I do the 4th power, and then I do the limit for t that goes to 0 in order to see what I have at that point. And what I get is something of this type. And if I started here, that was x, that was another linear form. This m was another linear form, t was my parameter. And so if I just see what I have in this tangent space, I have a form of this type. So I have x to the cube, that's fixed because I've completed the tangent space to the point x to the 4th. But then m is free because m is some linear form. So in this way, I just parameterize all the points of the tangent space of at that point. Okay. And so I'm just saying that all the points of the tangent space of that rational normal quartic at the point x to the 4th are x to the cube times some linear form. Okay. And that's precisely our guy. Our guy is when m is equal to y. Okay. Okay, and it's a tangent, it's a point on the tangent space. So our original W, it's one of the points here. And I didn't prove it now. I probably do it later, I don't remember. Being on a tangent space of this rational normal quartic prevents the same point of being also on a secant line. It's something that I've not seen here. We will probably see it later. But this, I mean, it's impossible that this guy will also have rank 2. Anyway. Here we are happy to see that the W tensor is a point on a tangent line on that curve, and is always the case because I took the 4th power to make an example, but you can run exactly the same thing by taking a d over here, and you'll end up with always with the same idea, except that here you would have x to the d minus 1. Okay. Yes, but this is coherent with the fact that our W tensor has border rank 2. It's not just a matter of the fact that all the 3×3 minors vanishes, 3×3 minus the catalytic vanishes, but it's also in a tangent space of that curve. And clearly, a tangent line, it's really the limit of a sequence of secant lines. Okay. Okay. There was a question? No. Okay. And now I define apolarity by using the same idea of these partials. And I define it as a perfect pairing between partials of order d and polynomial of the same degree. So it's perfect pairing. Then if I apply a partial of order d to an homogeneous polynomial of degree d, I end up with a number. And since it's a perfect pairing, I can use it to define the dual ring. So I may consider the space of partials being the dual of the space of polynomial of fixed degree, degree by degree. And now I define, I say that some partial of some order, it's a polar to F if this partial kills F. Okay, it's a pairing, so I'm just going in the pair of this. So an example, I take this linear form, I do my F, L to the cube. Okay, this linear form to the cube. And I take this partial here, it's the partial, where I partial 3 times by X. And if I evaluate this partial in L cube, this is non-zero, so this G is not a polar to F. But if I take this G tilde, that is 2 dy minus dx, and if you look at this, they are very cousin. Okay. And I apply this partial to this F, then I get 0. So this G tilde is actually a polar to this L to the cube. Okay. I just made this an example, just put some hint. We will go in this direction. Okay, and I also define the annihilator of F to be the set of all partials that kill my F. I fix my F and I look at all the partials that kills that F. Okay, I just use this perp, meaning that is what it kills F. It's not proper if you want to be strict in the notation, because when you do the perp, you use your perfect pairing, and the perfect pairing I defined was among 2 spaces of the same degree. So, but this is not, I didn't fix any degree. I'm just looking at the whole space of partials. Okay, it's just to remember that it's what it kills, is everything that kills your F, but it's not meant to be a subspace only of the space of partial degree D. This is really in the whole algebra. So all the partial of any order that kills your F. Okay. So in the previous example, the G tilde I wrote in the previous example belongs to F perp. Not only, but you can multiply your G tilde by whatever you want, and it still kill your F. Okay, because G tilde kills F. Okay, so also the ideal generated by G tilde is contained in F perp. Okay. Okay, so this is just to a second. Yes. So here I'm just saying, I just wanted to see that I really have that. Let's assume I have some linear partial in F perp with the same F. Okay. And I impose that this partial kills F. So who is this partial that has to be the apolar of F? If it's a linear partial, then I just impose this condition, some extra condition, and I end up that B has this B has to be equal to minus 2A. I just impose this condition, and this is exactly the G tilde I take out from my F before. Okay, and so also F perp is contained in this in the ideal of G tilde. That is really the ideal defining the point. So this G tilde defined is the form that defines the point 1, 2. Okay. And 1, 2 is really the dual of the coefficients of this. Yes. Sorry. So in this example.
Because you got it in the linear.
Yeah. Yeah.
It seems to me that as soon as G has to be greater than F, then basically anything be greater than the.
Yeah, you're right. You're right. You're right. You're right. You're right. 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 Yes, that's only for the linear function. Absolutely. Thanks. Thanks. Other remarks? for questions. This goes in on your comment. So this is a proposition that says, I just tell you, I have some f that is the power of a linear form. And I'm saying that then I can always find in the curve of my f the ideal generated by the point I have here. So the ideal of the linear form. And that's, I mean, just a baby example of this theorem. I like to call it theorem because it's very important, but it's classically known as the polarity lemma. And the polarity lemma tells that if you have some polynomial that is a linear combination of r powers of linear forms, this is an if and only if, with the fact that inside all partial that kills f, you may find the ideal of these points, of the forms defining this point. Okay. And the proof, one implication is easy. So if you have your f that it's some linear combination of powers of linear forms, you take an element in the ideal of this point, then G, since it belongs to this ideal, it kills all the Li's. So if it kills all the Li's, then it also kills your f. And so it's clearly inside f per. Vice versa, it needs some work. I'm just telling you, if you compute the space of the linear span of the power of these linear forms, it's not difficult to show that it's contained in the kernel of the perp of all these linear forms. And then you have to show that these two guys are the same dimension. They are linear spaces, and so you have to show that these two guys are the same. Yeah, these are the perp of all these linear. You just take them all. That's been the perp of L. You may think of the composition, or I mean the intersection. Yes, they are spaces. They are not okay. Intersection. Yeah, I just wanted to mean all of that. Thanks. And that's our key point. That's really all what we need and all what we use to go to where we want. I should have taken time. Okay. Okay, so keep this in mind. This is the most important theorem we will need. I can write my f in this form, if and only if in its perp I can find the ideal of these linear forms. Okay, and that's what we need because we want to write f as the sum of r pure powers. We look for the minimal possible r such that this is possible, and so we are going to find a way of finding, and we have our f. We will have to compute f perp, and then we will have to find a way of finding an ideal of some points inside this guy. Okay, this has to be our strategy if this theorem is okay. So let's see what we have to do. The first thing that we have to do is to compute f perp. But this we have a way of computing f perp. F perp is the set of all partials that kill my f. Okay, so we have a way of doing that, right? So we have catalecticants. Catalecticants, they go from the space of partials into the space of polynomials. So the kernel of these catalecticants are the partial that kills my f. Okay, so that's not difficult to be computed. I have F, I have a bunch of linear maps, and I have to compute the kernels of this linear map. That's easy. So this idea has to be contained in the kernel of all these partials. Okay. So we have that. If we go for this strategy, we have to compute the catalecticants, and it may happen that the rank of the catalecticant is maximum, and so I don't find many information from my partials, or then the rank of the catalecticant, they are equal after a certain index, and so that will be the point where I will start seeing some partials. Okay. Let's do examples. I take this polynomial here that I build up as a sum of two cubes. I compute this catalecticant here, so from partials of order 2 to polynomial of degree 1. And it has rank 2, it cannot be bigger. And now I look at the kernel of this map, and in the kernel I have this vector here. This vector is an element of the domain where partials of order 2. Okay, so this is an element of this space. Okay, I just renamed the variables because I'm lazy. I don't want to write every time partials off. I pull u0 and u1. And so this vector, after having fixed some bases, corresponds to, let's say, minus u0 square plus u1 square. So the basis will be u0 square, u0, u1, and 1 square. And if I look at this polynomial, I can factor this polynomial in this form. And so the ideal defined by these points is defined by this form, defines 2 points, 1, 1, and 1 minus 1. And again, if you look at these points, you exactly get these two. These are the same coordinates of the previous points. Okay? So L1 is going to be x plus 1, and L2 will be, no, sorry, x plus y, and x minus 1. There are many typos, sorry. So I found, how did I do? I computed the kernel, I found an element in the kernel, and this element defines an ideal of 2 points. These 2 points, so it's an ideal that is contained in that curve, and so these 2 points are the 2 points that I'm going to use to compute the rank of that, the decomposition of that.
There should be a
That should be a cube. There are many typos. Thank you. Many, 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 many typos. I can make a prize for who can get more. Most of my typos. I want to stimulate your attention. I'm sorry. Okay. So let's go for our friendly guy. This is still again the W tensor. Let's see what happens for this guy now. So I go for one of the most square catalecticants that I can make. It has degree 5. So let's start with C23. We already know that we expect this to have rank 2 because it has border rank 2. So this will have rank 2. And indeed it happens. Now I look at the kernel of this map, and in the kernel of this map I find this vector here. So it's the catalecticant that goes from partials of order 2 to polynomials of degree 3. So this is an element in the space of partials of order 2. And again, I fix the basis u0 square, u0, u1, u1 square. And so this is saying that I have u1, this is the polynomial u1 square. Okay. if this is a polynomial U1 square, which is the points that it defines, well, it defines the point 1, 0. It's one point only. While this is saying that this polynomial doesn't have rank 1. This matrix has rank 2. So this polynomial will not have rank 1. I computed this catalectic and I found this guy here, but it's one point only. I need to find at least 2 points, but I can't because this guy has multiple. Okay, it's 1 point and it's counted with multiplicity 2. Okay. So this is not telling me anything on the decomposition of this. I went to the most square catalectic and I realized that at rank 2 as expected, but the kernel of this matrix is not telling me anything. Because I found only 1 point instead of at least 2. So it's the most square catalectic, and so it's the good one to tell me the minors, but maybe it's not the one with the biggest kernel. Okay, I can keep going and see if I find a bigger kernel and have more chance of finding some more points in a bigger kernel. So these are just a summary for the equations of the second variety of the rational normal curve. I don't know why I put it here, but we have it, so let's do it. So this is just a test if you want to say if your polynomial has border rank 2 or not. We understood it already, so I started my point. If it belongs to the rational normal curve of degree D, it has rank 1. And otherwise, if it belongs to sigma 2, then it's either of rank 1 or of rank 2, or it's a point in the closure, okay, of the second variety. Okay, so this is the variety, everything. These are the polynomials of the tensors of rank 2, and I take them out, so I just have the points on the closure. And so we saw that these points are of this type, L d minus 1 times n, so linear forms to some power d minus 1 times another linear form. So these are only the 3 possibilities that you have if you have a point in sigma 2. Either it has rank 1, or it has rank 2, or it's a point of this type. And in all cases, if it has rank 1, then the catalecticons, they all have rank 1. And if it has border rank 2, then all the catalecticons will have rank 2. And this is a way of seeing it, because if it has rank 2, then it's a sum of 2 powers of linear forms. Then you have to fix some basis in your space. And why don't you take a basis made by these 2 linear forms? So you take L1 to the D, L1 to the D minus 1 and 2, and then at the end L2 to the D. In this basis, your second catalecticon will be always of this form. The catalecticon on this polynomial will be always of this form. So it's clearly of rank 2. And you will do the same for this polynomial here. This is a point on a tangent line. This is again your W state. You choose the same basis over here. And in this basis, this polynomial will always have a 1 over here and a 1 over here. Okay, so again, it will have rank 2. So for the second variety of rational normal curve of degree D, okay, you have a test that are the 2 by 2 minors. We already knew this is just a different way of saying this. I have only these 3 classes of polynomial, rank 1, rank 2, or points on the tangent, and clearly the catalecticons, they have rank at most. Okay. Okay, so we've just proved that for all possible elements in sigma 2, the rank of this catalecticon is at most 2, and so sigma 2 is contained in the space of these 3 by 3 minors. And also the other inclusion is true. And so the ideal of this variety is the 3 by 3 minors of this. This is, you can generalize this, and you might say that the ideal of the secant variety, the secant variety of the rational normal curve. So again, our polynomials in 2 variables only. Okay, this is generalizable, but only for this case of 2 variables only. Then you may look at the r+1 minors of the most square catalectica. Okay, so this minors that tells you the border rank of your polynomial in 2 variables. Okay. Okay. And again, here I'm still struggling around the same question. So if in this variety I really have to take this closure, and it's true already for the second secant variety, how can I distinguish if a point, once I've discovered which is its border rank? And that's easy. I go for the most square catalectic and I compute its rank. This tells me the border rank. And then I have to distinguish if it is a point of also rank equal to the border rank, or if it's a point on the closure. Okay, I'm still struggling on this one. Okay, so we have already said that it's via this polarity lemma. Okay, I think I already said all these things. I'm just repeating. Okay, so that's the original version of the Sylvester algorithm. Then you have your f of the KD in 2 variables, and you want a symmetric rank and the decomposition of your f. So the original version was start with I equal 1 and compute the first catalecticant. If this is rank R, then if R is equal to the I you started with, then you may say that your f is in the sigma R. Otherwise, you start again with I plus 1. But we already know that you don't have to do all the steps starting from 1 to 2 and so on. You go directly to the most square catalecticant, and then you immediately get the starting rank you have to start with, and this is the border rank. And then you compute the, once you've found the catalecticant that has the minors that tells you the border rank, you compute the kernel of that catalecticant. And if in this kernel you may find an ideal of R distant point, where R is the rank you get for that matrix, okay? If you find it, then you're done, because you have found the decomposition of R distant points. Okay? And so you have the decomposition, and then you have your f equal to the sum of Li to the. But if you don't have it, what this algorithm does is, let's try with R+1. With R+1, you still have the same rank for the next catalecticant, but maybe the kernel is bigger, and maybe there are some points in that ideal. There are in that ideal R+1 points that there were not in the previous kernel. Okay, and keep doing this until you find them. This is the original version of the Sylvester algorithm. We can do better, and I'm keep going with the same example, my favorite running example. So we already know, so this is again the double tensor in degree 5. We already know that the rank of this catalecticant was 2, and so the next one is 2. And we already seen that in this kernel, I couldn't find the kernel at point u1 square. Okay, I couldn't find 2 distant points in the kernel. Okay. So I go for the next catalecticant, that is C32, and I'm just telling you that you won't find the right number of distinct points in this in this catalectic. Let's go for the next one, C41. C41 is this matrix here. And in this matrix here, I look for the kernel, and this is the kernel. And now I take some generic element here. I just made a combination of these three vectors. This typo is U0. And in this polynomial, it factors in this form here. But again, I don't find four distinct solutions there. Yes, because this is a double root. Okay, so now I'm looking at C4. I aim now for four distinct points. Okay, this polynomial has degree 4, so it has some chance of having four solutions, but indeed two of them are the same. I really want four distinct points. And so I'm left with the last one, that is C51. And this is the partial of order 5, C50. And the matrix is just this matrix here. And in the kernel, I have plenty of things except this vector here. And now I write down a generic element in the kernel. And the generic element in the kernel is, for example, this guy here. And now I should look for 5 distinct solutions. If I'm not able, I ask some computer to help me. And I just have to cross finger that 2 solutions are not very close to each other, because then I may be not able to say if they are same solution or really 2 distinct solutions. But in this case, I can find 5 distinct solutions. And so I was looking for 5, and I get 5 distinct solutions. And so now I can claim that this guy here has rank 5. And this is the W tensor of order 5. So it has border rank 2 because these catalectic and they have rank 2, but that guy here now is rank 5. Okay. Okay. So far, so good. Questions? There are no stupid questions. Please.
That's for 2 variables.
Yes, only.
And so what's the complexity of the algorithm as a function of the degree?
As a function of the degree of f. So up to now, so this is not the last version of the algorithm. The algorithm can be better than that, and we will see it. And up to this case, this is the original version. Let's try every time until you reach the right one.
But you know that
In what we are going to see next, for 2 variables, if you know the border rank, then you just have to check if the rank is equal to the border rank, and if not, that's what we are going to see in the next slides. If it's not, you know which is the rank, and so you know directly which is the catalectic and you have to compute. And so at the end, you have only to try to solve to find the solutions of 2 polynomials. So you have to compute the minors of some catalectic and to compute the rank, and then you have to compute the solutions of a polynomial of the degree equal to the rank you found. If that works, it's fine. Otherwise, you go for another degree, that is d minus r plus 2. We're going to see it, and that has to work. So this was just to show the original version of this algorithm, but we don't have to make all these tries to reach the right rank. Okay, I just wanted to do this with you to see, I mean, step by step, how this can be built. But there's a better strategy. Just go directly to the right rank. But I didn't tell you yet how to get it there.
So about the complexity, it's one maybe D4, the other one D.
Okay.
Can we can maybe, well, we can improve with using the empirical structure of the square times symbol.
Does any of this work with the real case?
So I think that this works also with the real. I don't know about the, so the next step. After this, I think it works also. So I don't know the next step. I don't think so. The next step works so. Okay. And that's where I wanted to go. There is a more efficient algorithm that tells you exactly where to go. And I'll do this first for this guy here, and then we can try to generalize it. So in this example, I knew that the border rank was 2, and then I start checking if the rank is 2, if the rank was 3, if the rank was 4, and then I was happy at the end of saying that the rank was 5. Is there a way of saying, well, I have this double tensor, I go directly to 5? Okay, and that's precisely the content of this. So since I know that this guy belongs to sigma 2 and is not of rank 2, can I go directly to the right rank? And more general, once I know the border rank and I test that it doesn't have that rank, can I go directly to the right rank of this guy? Sorry. For the rational number, the gap is over. I can tell you. Okay. Yes, this was just, sorry, this was just to, I went back to the previous example, the W tensor written in terms of Segre, where we discovered that the rank was 3. Okay, so that was the W tensor of order 3, and the rank was 3. The example we saw yesterday. In the example we have seen today, this guy was of order 5, and the rank was 5. Okay, that's not a chance. Yeah, so I just do again the computation for the W tensor of order 3, just to check that also here is of rank 3. And this pentalecticon has this this guy in the kernel. Again, I don't see the 2 distinct roots, but I do the next one. And the next one is this kernel, and this polynomial in the kernel, it have exactly 3 distinct roots. So also in this way, you can prove that that the W tensor as rank 3. Okay, so I also want to see that it has rank 3 in a more geometric way. So I have my Veronese embedding, sorry. And we said that that guy was a point on a tangent line of that curve. That curve is a rational normal cubic. It has degree 3. By degree, as a definition of a degree, you may take a generic hyperplane in the ambient space, and the generic hyperplane will cut your curve in a bunch of points. And in this case, it will cut your curve in 3 points, and so the degree of your curve is 3. And the way you just plug you just intersect any hyperplane with the curve, and you end up with a solution with a polynomial of degree 3 in one variable. And so if it's generic, it will have 3 distinct solutions. And so if you have the Veronese map of order D, and you look at the Veronese curve, one normal curve of degree D, it will always have degree D, and the same proof works. You take any hyperplane, intersect with your curve, and then you have to solve the polynomial of degree D. And if it's generic, it will have the distinct solutions. So this is to show that the rational normal curve of degree D, it has degree D. Okay. 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 So at some point, okay. Yes, at some point I told you that the fact that the W tensor belongs to a tangent line to the rational normal curve prevents you to belong also to a secant line. This prevents that guy to have rank 2. And before I just told you this, and now I would like to see this with you. So this is again, the W tensor in order 3. It belongs to this tangent space. This curve has degree 3. Now I take an hyperplane in the ambient space. This hyperplane is going to be a P2 because the ambient space is a P3. And then I look at the intersection of this. So I take an hyperplane passing through my F. That is my W tensor. Okay, and this hyperplane will hit my curve in 3 points because that has degree 3. And so if this hyperplane passing through my F intersect my curve in 3 points, it means that the rank of my W tensor is at most 3, right? Because the rank is really the number of points on the Veronese curve whose span contain my F. It's a P2. It intersects the rational normal curve in 3 points. These 3 points are independent. And so the rank of these points of my W tensor is at most 3. Okay? So the rank of this is at most 3. We already knew that was bigger than 2 because via the catalecticant, I didn't find 2 distinct solutions when I should have found them. So that I knew that the rank was not 2. This argument tells that it's at most 3, and so it's 3. Okay, in a more geometric way. So now I want to do the same game, but with any W tensor of any order. So this is a point on this tangent line, and I can repeat the same argument that I did up to here. So this curve has degree D. And so I pick a plane through my point. I take a generic one passing through it to get my curve in D distinct points. The hyperplane in for this space, it's a PD because it's a P It's a PD minus 1. Sorry, there's another typo. It's a PD minus 1 because the ambient space is a PD. Rational number curve span a PD. And so this hyperplane is a PD minus 1. Okay. It's a PD minus 1. It hit the curve in D points. These D points are independent. They span this PD. And so again, this is a polynomial belonging to this, the PD minus 1 spanned by D points that are on the curve. And so this polynomial has rank at most D. I can write it as a sum of D points on the rational normal curve ability. So its rank is at most D. Okay. Now I can conclude because if I run the same argument before, the catalepticon tells me that it doesn't have rank 2. But between 2 and D, if D is not 3, there's a gap. Okay. And now I want to see with you that the rank is 3. D, sorry. Okay, so that if I have a double tensor, then its rank is always D. We proved that it's at most D, and now I want to prove that it has to be D, and so I assume that the rank is not D, so it's smaller than D. I would like to end up with some contradiction. So assume if the rank is smaller than D, it means that there are D minus 1 linear forms. Maybe they are abundant, but if there are less, there are also D minus 1 linear forms. Such that if I raise their power, okay, I take their span, they have to contain my F if their rank is smaller than D. Okay? And so it means that I have this D minus 1 linear form, I raise the power, I take the span of this space has to hit this line. Because my W tensor belongs to this line. Okay, so I have the tangent line that intersects a PD minus 1 spanned by these points. There are D minus 1 points, the PD. And now, so the ambient space is a PD. Okay, I have a line and I have a PD minus 2. Okay, so in PD they intersect if and only if the points that they span, the points that span and the points that span this space, they are linearly dependent.
I didn't mess up, but why can't we use border rank to found the rank?
The border rank is 2.
Okay, so that's yeah.
If D is 3, it's what I did before. But if D is higher than 3, then I have an argument that tells me that it's bigger than 2, an argument that tells me that it's more or equal than D, and I need something. And now I want to prove that it's really D. So I say, assume it's D minus, if it's a most D minus 1, I can always find this 4. Maybe I need less, but I just take them. So I have this, I just said that there has to be an intersection between this line and the space. And in PD, if these two guys are intersected, means that the points that they generated, they have to be linearly dependent. So the points that generate the space, they are easy. I just take these spaces. And for this one, it's a tangent space. It's a tangent space to my rational normal curve. So as generator, I take x to the d and the tiny variation of this point. Okay. You may also think of this point as a double point, but I didn't want it to enter into the scheme notation. Okay. So for people that like schemes, you might take this point as a double point, like a 2-jet. But I don't want to enter this argument now, so I just want to generate this line with this and the tiny variation of this one. And so I'm saying that all this d minus 1 plus 2 points, so d plus 1 points, they have to be dependent. But they are d plus 1 points on this curve. Okay. And now I claim that on this curve, d plus 1 points are never dependent. They have to be linearly independent, and it's easy to prove this. Are you with me up to here before I pass the next slide? If this happened, this d plus 1 points have to be linearly dependent. since they are all belonging to this curve, my next claim is that this cannot happen. So my claim is that any choice of d plus 1 point on this curve is linearly independent. And the way of proving is very easy. Any point on this curve has its own parameterization. It's a point on a rational normal curve. Okay. And then if I want to check if they are dependent or not, I put them in extraordinary matrix, but it's a Vandermonde, so the determinant is. And so they're actually linearly independent. And so I just proved that it's not possible that any choices of d plus 1 points on that curve are linearly dependent. And so it's impossible that this line hit this space. So it doesn't matter how I choose d minus 1 point on this rational normal curve, they will always span a PD minus 2. And there's no way that this PD minus 2 hit a tangent line there, except if you take exactly that point. Okay. So it's impossible that that rank is smaller than d. Okay, so this really concludes the proof. With this, I prove that the rank is d because it cannot be smaller than d. But if I take any hyperplane through my point, it will hit my curve in d points. So I have a presentation of my W tensor as a sum of d powered of linear forms. And I prove that it cannot be d minus 1. Okay. So now I know what to do if I have a point of order rank 2. So for belonging to sigma 2 of CD, I can check it by checking the 3 by 3 minors. And now either it has rank 1, so the 2 by 2 minors vanishes. Or if not, then I know it can be either a point on an honest secant line or a point on a tangent line. If it's a point on an honest secant line, we saw that it has rank 2, and I can find that I can discover this by looking at the kernel of the second catalecticant. And if in the kernel I find 2 distant points, then I can conclude that this guy is actually rank 2. If not, I have only one possibility. It belongs to the tangent line. And if it belongs to the tangent line, then I just prove that its rank has to be d. Okay? And so I don't have to check all the possible catalecticant between 2, 2 and d. I know that if it's not 2, then I just go to d. And I go directly to the catalecticant d0. And here I have to find the distant points.
So, and for every of W sets,
Every
of these W sets is fine. But I also know that the tensor product W sets, so that's the find that rank, but only upper bound. Where does the complexity of this, what makes the tensor product of W stage, of which we always find the rank, make it more complicated such that you cannot find.
So I know you know this. So once you make the tensor product of 2 W tensor, of course you have an easy upper bound of their rank, that is the product of their rank. But you know there are examples where this bound is not reached, that the product of this W tensor has a rank that is strictly smaller than the product of their rank.
Or maybe there's
Yeah.
maybe there's.
So I worked a little bit on the question you asked me, and so there are some geometric conditions that tells you that then when you start making modifications of this W tensor, you may certify that certain geometric condition happens, then the multiplicativity is not certain, it's strictly multiplicative. But I can tell you that I have only few geometric conditions that tells you that if this thing happens, then it's significant, but I don't have any value. So I don't have a nice characterization like this. This is the property that tells you the rank. So I know that there are some things, some geometrical things that they happen, then the drops, but I don't have I think it fits the way wide. Okay, so now we can refine the algorithm and just say, okay, I have my polynomial in two variables. I want to see the rank and the decomposition. And then I compute the kernel of the most perfect catalecticant. If the rank is 1, then the rank of the catalecticant is 1, then the rank of F is 1. I pick any element in this kernel, and I found the linear forms whose power is my F. If the rank is 2, then the border rank of F is also 2. And then in this case, I just have to go and pick a U in the kernel of the second catalecticant. I find two distinct solutions. If the border rank is 2, but the rank is not 2, then I just go directly to rank D, and I go directly to this catalecticant. And this will have to reveal me these points. If the rank is bigger than 2, then I just say that the border rank is not 2, and up to now, I just have to keep going like this. But I'm going to do the next step also for other border ranks. I just summarize what I've seen up to now for sigma 2. Yes, this should be my last thing. I think I can do this in time. So now I want to prove that if I have a polynomial in two variables, and I know its border rank by the minors of the catalecticant, then its rank is either R, so equal to the border rank, or it's D, the degree of my polynomial, minus R, the border rank, plus 2. For R equal 2, so border rank 2, this is coherent. It's D minus 2 plus 2, what we have seen before. And I just want to prove that if the border rank is R, then the rank is D minus R plus 2. And I'm going to do in a very geometric way. So if the border rank of F is R, then it belongs to the secant variety. And yes, it belongs to the secant variety. So the rank can be either R if it's in sigma R, and that's obvious. And so I really want to see what happens if I take something in the closure. Okay, that is not of rank R, so the rank is bigger than R. Okay. Now it's not like before. Before I had sigma 2, and so in the closure I had only tangent lines. Now I have sigma R. I have to discover what I have in the closure. Okay. So the rank of F is bigger than R. Now I try to mimic what I did before. Okay. So if the rank of F is bigger than R, and the border rank of F is R, then I have some space of dimension R that is the limit of a sequence of some PR minus 1, which are R secant to my CD. So I have my Gaussian curve over here. Okay, I take R points on that curve. They span some space of dimension of it spans some PR minus 1. I look at some sequence. Okay, and if my point has border rank R, then there is a sequence of this that reach my point. And so what it happens, this works only for curves. Okay, so for curves, it happens that if you look at this sequence, all these linear spaces, they intersect your curve in distant points. And if you allow yourself to move on this curve, when you go to the limit, there you have that it may happen that 2 points, they go together. Also more than 2 points can go together. Okay. But this is what the phenomenon that happens, that you have at least 2 points going together in the limit. And so my H, the space here, that is the limit of a sequence of PR minus 1 that are R secant. This H is not R secant, meaning that it doesn't intersect my curve in exactly R points intersect, as I count the number of points I have less than R points. But if I count the multiplicity of them, I get R. So some point has to be at least double. But I can have different things, right? I can have 2 points going together, 3 points going together, 2 here and 4 here, okay? Many things can happen. The point is that I have at least a double point. And so now I call my Z the intersection of H of this space with my curve. And I want to keep track of this multiplicity now. So if I have at least 1 point of multiplicity 2, I want to keep track of this. Okay? So in the notation as before, you may think this as P and a little variation of this point P, or if you like scheme, this is a point of length 2. So Z is is not the span, sorry. It's just the set of this point with this one counted group. Now, I don't know which is the rank of F. I assume it's some number K. So if the rank of F is K, whatever it means that there's some other linear space that intersect my curve in K distant points. Okay, this is going to be a pk minus 1. And so my F belongs to this pk minus 1 span by this points over here. But since my F also belongs to the space of the limit, it belongs to the intersection of these two spaces. And now I'm arguing exactly as I did before, because now I have two spaces, two linear space that intersect in a point. And so the points that generate the space, they have to be linearly dependent. Okay? And I already know that they cannot be in total d plus 1, because d plus 1, they have to be linearly independent. Okay, so here I have counted the multiplicity R points, then these, they have to be at least d minus R plus 2. If here I have R points, d plus 1, they have to be independent, so they have to be at least d minus R plus 2. But this is exactly the number I want to reach. Okay, in my statement, I add that the rank is either R or d minus 2. So I already found a way of building this number of points. I'm out of time. Yes, okay. Now I need to just find the other inequality. And the other inequality, now I want to prove that they are exactly d minus R plus 2. And I'm doing exactly as sorry. So a way of proving that this is exactly this pressure makes me. A way of doing this is to exhibit that I exhibit exactly this number of points. Okay, and in a way I did it because I took a plane and I said, okay, I have this k points. But well, this is probably kind of doing in 1 second. So if the rank, I want to prove this inequality. And now I consider the space spanned by all the points I had before, the blue ones, but those where I have this multiplicity here, okay? And F. So this green guy here is spanned by these points and F. Okay? And of course, F does not belong to this space because it belongs to the blue one. And now I consider all the hyperplanes that contains the pass through F and that contains this green space here. Okay. These are hyperplanes, so they have to intersect my my curve in D points. Okay, and now I just have to count them because here I have R minus 2, and so this hyperplane will intersect this curve in other D minus R plus 2 points. And by construction, the span of these other 2 points will have to hit my F. And I think I close it. I mean, it's more fine, but I think I close it here. So the efficient version of my algorithm is go for the most square catalectic, and this reveals the border rank. check if the rank is equal to the border rank by going to the same catalecticant of the right rank by finding our solution. If not, go directly to the rank d minus r plus 2. So go directly to this catalecticant over here. And this will have to reveal you the rank of. And yes, so here are some examples. Yeah, I have some summary. And so what's next? So I told you the story for polynomials in two variables. Of course, you may be interested in what happens next. And I think that this really will be the main content of Bernard's, I think. The point that I want to stress is that everything here was possible because I always had some catalecticant big enough to reveal me something in the kernel. So as soon as I have this most square catalecticant that cannot reveal me neither the border rank, for example, then I cannot do anything. Okay? So, but I don't want to spoiler too many things. I stop here.
Thank you.